All right. So over Christmas, my son's 11, so he watches a lot of YouTube videos, and he really had to show me a couple of them, and so it makes me really want to now, like when I record class, to say, hey, if you like what you see today, smash the like button. It helps out the channel a lot. Really helps out the channel. So if you like the content, subscribe, like. So anyway, do a giveaway. 250th subscriber. So all right. Yesterday, we introduced the concept of waves. So first, let's describe a wave, right? What is a wave?
It's a disturbance of matter.
A motion of a disturbance. It's a disturbance in matter. But maybe more importantly than what is a wave, what does a wave do? It carries energy from one place to the other, right? So yesterday, we talked about two types of waves, right? Or actually, well, sorry, first, we talked about one type of wave that we call a mechanical wave. So, what does it mean to say that something is a mechanical wave? It travels through a medium, right? So something that there has to be something to fill the space, okay? And then we talked about two specific types of mechanical waves. So tell me about one of those types of mechanical waves. A transverse wave. And Kara, what makes a wave a transverse wave? Wave causes the medium to vibrate at right angles, and so we use the spring to sort of represent that, okay? Actually, maybe the other one, like the seismic wave, while it's not a specific type of wave, it is an example of the other type of wave, and that other type of wave is a what? You want somebody else to take it from there? Yeah. A longitudinal wave, all right? So seismic waves are actually examples of longitudinal waves, all right? And a longitudinal wave, right? What makes it a longitudinal wave? Go ahead. Parallel direction of wave movement, right? So crunch, spread, crunch, spread, crunch, spread, as opposed to up, down, up, down, up, down. Okay, good there. All right. I asked the other class this. I asked the other class, and they gave me the answer that I wanted to hear. So I'm going to ask you guys this. Yesterday, when we were doing the wave stuff, it seemed to me as if you guys had learned a lot of that stuff before. All right, like that you had, the different types of waves and stuff like that. How about if I give you things like period, frequency, amplitude, wavelength? Are those things familiar? Yeah. Do you remember what they are, or have you heard them before? And you, okay, so all right, so we'll go over those today. And that, okay, okay, all right. So to start off today, I'm not sure what this is, but oh, it's something about to expire. Okay, all right. To start off today, I want to start you guys off with a video. And at this point, I just want you to watch. It's a cool video, but it does introduce some of the things that we're going to talk about today. So maybe you've seen something like this before. They actually have one of these down at the Science Center. So if you've been down to the Science Center before, you may have seen an actual demonstration of this. But this one is called Pendulum Waves, and it stars some guy named Alan. Okay? So. Oh, yeah. Oh, no. All right, so we'll see Alan here in a second, or maybe, yeah, there's Alan, I believe. So. starts all over again. It doesn't show you the whole thing again. So just all right. Well, this channel is, if I remember correctly, Harvard Natural Sciences. So I mean, they've got. I don't think they need my endorsement to get traffic. I think they're probably pretty good on their own. So, all right. So today, wanted to spend some time talking about how we distinguish waves from one another, how we describe these waves, how we describe individual waves and how they differ from one another, and talk about their properties. But we'll see that a lot of times the terms that we use here to describe these waves are related to some other motions. And that other motion that we talk about a lot is called periodic motion. So if we talk about something that's periodic motion, we describe something that happens at regular intervals, right? Things that keep happening over and over and over again. And here, this is an example of some periodic motion, right? There's actually two periodic motions that occur with the Earth, right? What does the Earth do periodically? It spins, right? It revolves, right? Sorry, it rotates, right? But then it also does what? It also revolves, right? When it spins on its axis, we call that what? What do we call it when the Earth spins on its axis one time?
A month.
That's a day. That's a day, right?
The moon one's a month.
The moon one is a month, yes, all right, okay. And then it's not exactly a month, but it's close, right? And then when the Earth revolves around the sun, that's a year, right? Okay, so, but both of those happen at regular intervals, okay? So, while we described a wave before as a transfer of energy, we didn't describe what we have to do to create a wave. So, what do we have to do to create a wave? Oh, hit something, create a disturbance, and more specifically, what does that disturbance have to do? It has to do work, right? Because work is a transfer of energy, okay? So, if we have a disturbance that happens continuously, it continuously does work, or sorry, continuously isn't the right word I wanted to use. If we have a disturbance that happens periodically at the same interval, it will do work at the same interval, and it will create waves at the same interval. All right? So the description of the periodic motion also describes the waves that are created by the periodic motion. So today, we're going to use these pendulums to help us describe the waves. All right? Now, you might think, well, wait a second, that pendulum just goes back and forth. And that's true. But if we have a pendulum like this one in the picture, okay? That pendulum in the picture is made of a funnel, and in that funnel is some sand. And so as the pendulum swings back and forth, sand falls out of the funnel. But this part here is a rotating table. Oh, sorry, a conveyor belt of a table. And so as this conveyor belt moves to the right, the sand gets dropped on the conveyor belts, but the next sand that gets dropped isn't in the same place because the conveyor belt has moved, right? End result, what have we created on the conveyor belt? A wave. Specifically, what kind of a wave? It's a transverse wave, right? So we can see how this pendulum, the movement of the pendulum, actually does relate to wave behavior if we can see the end result of it. All right? So let's talk about how we describe periodic motion, and then we'll talk about how that relates to waves. So the first thing that we use to describe periodic motion is the period. And based on the representation of that period as a capital T, right, you might be able to guess that the period tells you what about the periodic motion? It's a time, right? And so the period is the time that is required for one full cycle of motion. or the time that it takes that object to return to its starting position. So if we use the pendulum, right, if we let it go from back here, it swings forward, it swings back, the time that it takes all the way to get back to the starting spot. So from now to now, right, that's one full period, the time that it takes for that to occur. Okay? Good there? And if we're talking about waves that would relate, or waves that would be created by this periodic motion, right? One full cycle from back to front to back again would relate to how many waves? That'd be like one wave, right? So the period is the time for one cycle, but it would also be the time for one full wave. Good there? Yeah. All right. Sometimes, though, especially if our periods are very short, it's not as easy to measure the time for one wave, but sometimes it's easier for us to count. And so we describe the frequency, right? Based on the definition of frequency, if we measure the frequency of something, what are we measuring? How often, right? How often does it occur, right? Which is not unrelated to time, right? But a frequency is the number of cycles that occur in 1 second. Technically, you can measure that frequency over any period of time. We just sort of like standardize it to 1 second. We use a unit called the hertz to represent frequency. And hertz is a derived unit that tells us the number of cycles that occur every second. All right, good there? So, two pendulums, all right? You're gonna let them go at the same time. Take 30 seconds, talk to the person next to you. Describe for me the period and frequency of these two pendulums. Not necessarily in absolute terms, but as they compare to each other. Frequency and period of these two pendulums. Go.
Have more cycles. Has a higher frequency because of
And then the other one takes a long time to do.
but it's a shorter period but a higher frequency. Which one is the higher
All right. So, Henry, just because when I was walking by, I heard your description. It was a really good description. Right? So, how are you compare the frequency and the period of these two pendulums?
Well, I said the top one has a shorter period but a higher frequency, and the bottom one has a higher period but a shorter.
Okay. Are we in agreement with those two things? So we see how that's right? Okay. So, that being said, what kind of relationship do frequency and period have? They have an inverse relationship, right? Frequency and period are inversely related to one another. If one goes up, the other one goes down, and vice versa. Good there. Good there. All right. The frequency relates to the disturbance, or in this case, the pendulum. But the disturbance is causing the waves. So, right, a wave's frequency is the same as the frequency of the vibrating source that produces that wave. A wave's frequency matches the frequency of the vibrating source that produces that wave. That also means the wave's period matches the period of the vibrating source that is producing that wave. So, in my hand, I have a tuning fork. Okay? Tuning fork is used to produce sound of a consistent frequency. All right? So, when I hit the tuning fork, that causes the arms of the tuning fork to vibrate back and forth. Okay? You couldn't see that in the video, but I don't know. All right, but as those arms move back and forth, what do they run into? Matter, specifically what matter? The air that's in the room. And as that arm moves, it pushes the air. And that means it's doing what to the air? Transferring energy, or it's doing work on the air, right? And if we do work on the air, that means we create a wave in that air, right? But because those arms are moving back and forth at a certain frequency, the waves that are being created have that same frequency. This tuning fork is a 320 hertz tuning fork. So these arms vibrate back and forth 320 times every second. And that then creates waves that have a frequency of 320 times every second. Okay? Anybody like have perfect pitch and they can tell what note this is? Good guess. I mean, there's lots of C's on the piano, but this is not a C. You know, C flat. No, it is not. There is no C flat. This is an E. So, okay. 320 hertz is E. Okay. All right. So this one. All right. Okay, so two things. Let's talk about the science first, right? Okay. So several of you noticed this is a higher pitch sound. Okay, I think maybe you're familiar with this. Higher pitch relates to what? Do we know? What higher pitch relates to higher frequency? Higher frequency waves are registered as our ears as higher pitch sounds. This is a 480 hertz tuning fork. Really?
Sounds like an elevator.
Yeah, it's definitely lower than a G. It's
There's higher pitch.
Really? I passed the hearing test in 3rd grade. Thank you very much.
We just did it right. Yeah, we just did it like a week ago. You guys all failed.
Exactly.
It's lower.
It just like it sounds loud.
Is it really? Oh, I don't know.
We'll leave it up to our viewers to decide.
Comment down below.
It's like if you think the first tone is low. So this one on your right is a 480 hertz tuning fork, which relates to B. It's a B.
Oh, wow. This doesn't sound like a
I know, it just doesn't, yeah. Sure.
Comment.
All right. But, all right. So to show this again, let me show you a different video here. Okay. All right, so here, I muted this because I don't like the lady that talks in the video, so I just muted her. All right, so here, you guys are looking at a video of a water table. So here's a water table. It's a pool of water that's about this deep, about an inch or so deep. And that is right up here in the video. Okay, so it's a pool of water. And then this spot right here is a little arm that just goes up and down like this and does work on the water and creates waves in the water. Okay? Up here, which you guys can't see in the picture, is a light that shines down through the water, and this white part right here is a screen that's just tilted so you guys can see the shadows of what's going on in the water out there. Okay? So, as the arm is bobbing up and down, doing work on the water and creating waves, we can see those waves. And the brighter spots that show up, those are the troughs of the wave because the light has less water to go through. And then the darker spots up here, right, those darker spots in between the lighter spots, those are going to be your crests, right? So, all right, she creates some waves like this, and she's kind of introducing that. And then here in a little bit, we'll see that there's definitely a change in those waves. So, we'll wait patiently for that to happen. Okay. Ready? It hasn't changed yet, so you'll know when it changes. So. There we go. All right. All right. So again, in order to change the frequency of the waves, we change the frequency of the source creating the waves. So now the arm is bobbing up and down more times per second, and that's creating more waves per second. Okay? But what are you seeing? How did we know that the frequency changed? What led us off onto that idea that the frequency has changed? So the amount of waves in that box, right, increased. But here you're not measuring a time. What are you looking at? How did you know that the number of waves increased?
The wavelength.
Right? The wavelength. The distance between each wave keeps getting, or has gotten smaller and smaller and smaller, right? Here, the distance between trough and trough is this far. But if we go back to this part of the video, right, the distance between trough and trough is this far, right? So, we talk about the time it takes, we talk about how many waves happen, but then we also talk about the distance between waves. And we use the term wavelength to describe that distance. We use the Greek letter, that's a lowercase lambda. It looks like an upside down Y. Okay. So we use the lowercase letter lambda to represent wavelength. So wavelength, like its name suggests, is the distance between the exact same points on two waves that are next to each other. In transverse waves, we usually measure that crest to crest or trough to trough. But you can also talk about the wavelength of a longitudinal wave by measuring the distance from compression to compression. Same idea, still measuring the distance between the same point on two consecutive waves, just a different way of describing it. The pictures at the bottom of the page right there summarize what I just showed you in the video as well, right? In order to decrease the wavelength, what did we have to do? Increase the frequency, right? So, what kind of relationship do wavelength and frequency have? Inverse relationship, right? So, measuring or increasing the frequency will blank the wavelength. Decrease the wavelength. And that's what kind of relationship? Inverse relationship. We also talked about another type of inverse relationship already, right? What else did we say was inversely related? Frequency and period. Wavelength, oh, sorry, I should put that up. Right. Wavelength is the distance of one wave. What is the period? Time of how many waves? One wave. right? So period and wavelength are directly related. If we make the period longer, the distance from the next wave is a bigger distance, right? But they're both inversely related to frequency. Okay? Good there? All right. We have a way of describing the distance of a wave. We have the way of describing the time of a wave. Right? If we can measure the distance of something and the time of something, what else can we then tell about that something? The speed, right? If we know the distance of something and the time of something, right, that relates to its speed. All right? So let's drop down here and let's talk about wave speed. Okay? So, like its name suggests, the speed that the disturbance travels through a medium. Right? I know, we skipped the amplitude. We'll come back to it. All right, so to calculate the speed of something, what do we do? How do we calculate the speed of something? Distance over time, right? So there's two ways we can actually calculate the speed of a wave. The first one is we can take the what and divide it by the what? The wavelength and divide it by the period, right? So we can take the speed, or we can figure out the speed by taking the wavelength, lambda, divided by the period, capital T. Because wavelength is a length, period is a time, all right? But, so you guys might want to write that down because I forgot to include that on here, right? So it's lambda over T, right? Lambda divided by T. Or we can also take the wavelength and multiply it by the frequency. Because in order to turn, because they're inversely related, right? When we inversely relate something mathematically, what do? We just do what? Flip it over, right? In this case, period is on the bottom, so if we flip it over, that takes frequency to the top, so we can calculate the speed of something by taking its wavelength, multiplying it by its frequency. Okay? However, that speed is dependent on the medium through which the wave is traveling. The speed of a wave can change if it enters a new medium, or if the conditions of that medium change. So the speed does depend on the frequency and the wavelength and period, but it also depends on the medium through which that wave is traveling. Okay? Jenny, go ahead. That's going to be speed as well. We can calculate speed in either way, right? And then speed is v, right, with velocity speed. Yeah, either one of those will get you the speed of that wave, just depending on what we actually measure about it. All right, this last bullet point, the question that goes along with it, or the practical application, is for my marching band people. All right, so marching band people. Okay. Start off in the summer, right? And it's 90 degrees, you go march for 5 hours, like out in the parking lot or wherever, right? What? Yeah, 2, 3 days. 2 days. Yes, I know, but their time in band camp is longer than your time in football, so it is. So. Anyway, regardless of that. All right, but, so you do that, right? 5 hours a day, whatever it is, marching around 90 degrees, okay, so then, right? 3 months goes by and you come to the last game of the season, right? And now, instead of it being 90 degrees, now it's like 40 degrees, right? And what happens to the sound of the band? It sounds like crap, right? March like 5 hours a day, and 90 degrees, now we get here at the end, now it sounds like crap, right? It's not your fault. It's not your fault, right? What's different? from the beginning of the season to the end of the season?
Conditions.
The conditions are different, right? The waves that you're making by those musical instruments are traveling at different speeds because the air is a different temperature. And that causes changes in the frequency and the wavelength, right? So that changes how we perceive those waves because the frequency changes. It's also true of if you have like especially string instruments where the waves are actually created in the instrument itself, right? In a wind instrument, the waves are actually in the air inside the instrument. But in a string instrument, the strings are actually vibrating. Changing the temperature of a violin or of a guitar can actually change how it sounds. And so, what we do, right, we take the little tuning string and we make it either tighter or not as tight, and that changes the conditions and that changes the frequency. All right? All right, last thing. Nope. Amplitude. Okay? Taking this pendulum. I pull it back this far, it swings forward, it swings back. Great. Take this pendulum, you pull it back this far, it swings forward, and it swings back. Okay? Because we're running out of time, I won't do this, but if we measure the period of this pendulum, the period does not change depending on if it swings this far or if it swings this far. Okay? But the amplitude does. So amplitude is telling us a distance, but not the distance from wave to wave, but how far does each wave actually go. So the maximum displacement of the medium from the rest position. The rest position being like, where it starts before a wave comes back. If we want to increase the amplitude, what do we do? Well, how much energy? More energy, right? We have to pull that pendulum back farther. That's more work. So the amplitude of a mechanical wave tells you how much energy it is carrying. The bigger the amplitude of the wave, the more energy that wave carries. Okay? All right, tomorrow we'll look at a few more examples, a few more videos, and we'll talk about what happens when waves run into each other or other things.